Lauren, do you have any questions whatsoever about either the test or about relations or the equivalence relation stuff today?
Well, I didn't have any specific questions. I just thought maybe you would go over some stuff some more, but I didn't think,
Yeah,
like, I thought there'd be more people, so I didn't know.
yeah, me too. Is there anything in particular, like which section would you like for me to go over some stuff?
Um, Maybe if you wanted to talk about partitions
Yeah, sure.
for like a minute.
Sure. Right. So the basic theorem that we got to in 9.5 was this way of passing back and forth between an equivalence relation on a set and a partition on that set. Right. So the critical notion or the critical idea is that if we start with an equivalence relation, right? So we start with an equivalence relation, which I'll write as tilde, right, on some set. So I've got this relation on a set S, which an equivalence relation has three different things. Can you remind me what the three different parts of an equivalence relation are?
Hold on.
Yep, sure.
Oh, the symmetric, reflexive, transitive.
Exactly. So reflexive means that A is always related to A for all A and S. So every element is related to itself. The symmetric is that if A is related to B, then B is related to A for all A, B, and S. And then the last one is if A is related to B and B is related to C, then A is related to C um, for all A, B, C, and S, right? So there are these three conditions for all A, B, C, and S, right? So these are the conditions that we're familiar with for an equivalence relation. Is that okay?
Yes.
Okay, so the point is, from this data of an equivalence relation, we're going to build subsets of S called equivalence classes. So from this, we build equivalence classes. And what these are going to be, let's call it the class of A, which is this, I'll use this box notation. This is going to be equal to the set of all S in the set S such that S is related to A. Okay? This good so far?
Yes.
Now, the point is these sets break up the set S in a very nice fashion in what's called a partition of S. And so a partition, honestly, a good way to think about a partition is really just if you visualize some set S as some set, then a partition is just splitting off a bunch of subsets of S such that all of these subsets, they have no intersection and their union is all of S, right? So I don't really have space, but once again, a partition is a collection of sets BI such that the union of the BI is equal to S and BI intersect BJ is equal to the empty set. So it's like taking every element of S and putting it into a different box, basically. And every element has to go into some box. So is this good so far?
Yeah, makes sense.
So the point that I was trying to get, and the deep theorem, is that you can go back and forth. Anytime that you have an equivalence relation on a set, you can build these special subsets called equivalence classes, and these will partition your set. And you can check that these satisfy the rules of a partition. Namely, every element is inside one equivalence class, because every element is equivalent to itself. So every element lives inside some equivalence class. And then you can also tell that the equivalence classes are all disjoint, because if B is equivalent to A, and if you have two different equivalence classes like A and C, one of the things that I proved in the lecture is that the set, if A is not equal to C, if the equivalence class A is not equal to the equivalence class of C, then the equivalence class of A intersects the equivalence class of C is equal to the empty set. Right? If you're saying that something's equivalent to A and C is some different equivalence class, you can't also be equivalent to anything in C. So their intersection is empty. So from an equivalence relation, we can build these subsets called equivalence classes, and these partition our set. So I'll call this like the equivalence class of A, this is the equivalence class of B, etc. And then it turns out that you can go the other way. If you have some set and you have a partition on that set, then you can define an equivalence relation whose equivalence classes are these subsets, these elements of the partition. And I did an example in the lecture using modular arithmetic. I can go over that example again, or I can try to find a different example if you'd like.
I think that's okay. I understood the one in the lecture, I think.
Okay. Do you mind if I could do another example?
But sure.
Just for fun. So for instance, what I can do is I can set up, here's a good one. I'm going to first define a partition on the set of real numbers. So let's let S be the set of real numbers. And then let's let BI be equal to the interval including I and not including I plus 1, where I is in Z. Okay? So the first thing is to notice that the BI's form a partition, right? So the first thing to check is that every R in the real numbers is inside some B comma B plus 1. But this is true, right? Every number is either an integer or it's between two integers. If it's an integer, it's inside here. This contains an integer, right? If R is in Z, then R is inside B sub R. And if R is not an integer, it's between two integers, and you just pick the floor. This is like the floor function, essentially. Okay, so, and then moreover, BR intersect BJ is empty, right? Because if these are two integers, if R and J are not the same integer, then these sets have no intersection. So you agree that I have built a partition of the real numbers this way, right?
Yeah, I see it.
Right. So once I have a partition, then I can define an equivalence relation. I can define R sub B is a relation on R with S is related via the relation B. Well, I want to write this a little differently. I'm going to define a relation on R such that A, B is inside my relation if and only if A and B are both inside Bj for some j. Okay, so essentially what this is saying is this is the floor function. So it says take any real number and write it out in a decimal expansion, and then just chop off the decimal tail and only take the integer part. So like this is saying take 10.357 repeating, chop off the decimal tail, and this just becomes 10. Take pi and chop off the tail, and pi would be related under this equivalence relation to 3, right? It's just saying take the integer part of whatever your number is. And the point is that one can check that this relation that I define is actually an equivalence relation. Namely, A is always related to A, because if I take any integer, it's going to be related to itself, because they have the same integer part when you chop off their tails. It'll be symmetric and it'll be transitive. All those things will hold. So in this way, I went the other direction. I started with some partition of the reals, and I produced an equivalence relation. And the equivalence relation is the floor function, more or less. Like that's two things are equivalent in this equivalence relation if they have the same integer part in their decimal expansion. Any questions about this example? No questions about this one? Everyone's very happy with what I just did? Someone's got to give me something. Come on. Is my mic still working? Am I muted? I have no idea. Am I muted? Okay. So, yeah, here's another example of an equivalence relation. Someone should give me some guidance about whether I should explain more about this or whether I should move on to something else. Yeah.
I think you're good on this one.
This one's reasonable?
Mm-hmm.
Okay. So yeah, this is just the general pattern. Well, these are kind of simple examples of this actually quite deep idea that a partition on a set is equivalent to an equivalence relation on the set. And the way that you pass back and forth is if you have an equivalence relation, you take the equivalence classes, and those give you a partition. In the other direction, if you have a partition, you can define an equivalence relation whose equivalence classes are the subsets of your partition. Okay.
I have,
oh, yeah.
Yeah, I have another question.
Sure.
I'm gonna put it in the chat.
Sure.
And it's only one part of this. So do you want to? You could just go through it all, or I could like go through it until I get to the part that I want to ask my question about.
Let me just write it down
Okay.
and see where we are. So find smallest equivalence relation on 1, 2, 3, 4, such that the following elements are inside the equivalence relation. 1, 2 is in there. 1, 3 is in there. And, oh, all the way up to 5. And 4, 5 is also in there. Okay. So there are some easy ways and some hard ways of going about this one. What are your thoughts?
Well, I knew we were making an equivalence relation, so I knew it was going to be some kind of relation that was symmetric, transitive, and reflexive.
Right. So reflexive is a big one.
Um,
Is this relation? Well, okay. Keep going. Sorry, I'm getting.
and so I just started basically making it from the given set, and I knew it had to have those 3 tuples that were already mentioned.
Right.
And so I started with, having them be reflexive. So I knew it needed 1, 1, 2, 2,
Right.
3, 3, 4, 4, 5,
Exactly.
5.
1, 1, 2, 2, 3, 3, 4, 4, 5, 5. You need all these just so that you're reflexive. Yep.
And then I knew it needs the actual tuples that are given in that subset. So 1, 2, 1, 3, and 4, 5.
Right.
And then you need to satisfy both symmetric. So you would also need 2, 1, 3, 1, and 5,
Right.
4.
2, 1, 3, 1, 5, 4. Yep.
And
And
then
then?
you just have to make sure it's transitive too.
Right. And this is currently not transitive, right?
Can you go into why it's currently not transitive?
Yep, I can. Because I have the elements 2, 1, and I have the elements 1, 3. What would transitivity tell me that I need?
2, 3.
I need 2, 3.
Okay.
And I also need 3, 2 because I also have 3, 1 and 1, 2.
Huh.
Right?
Okay, that makes more sense. That was the last part that I was confused about, was that 2, 3 and 3, 2, where those came
Now,
from.
one would have to check, really. Once you did this, you'd have to check, oh, what we did here was we took the transitive closure of this relation, which essentially just means every possible way that you can set up 2 this way, make sure you include this guy. And every way you can set up these 2, make sure you include this guy. It's possible that once we add in, like if we take the transitive closure of something, that doesn't mean that it's symmetric or that it's reflexive. So we'd have to check once again that this set is reflexive. Well, it is because it still has these. And now we need to check that it's symmetric. If I have 2, 3 in there, do we have 3, 2 in there? Yes. If we have 3, 2 in there, do we have 2, 3 in there? Yes. So this process of taking closures of relations is a way to go about this, but you have to check things maybe a couple times. Can I
Okay.
offer you a more straightforward way of seeing what's going on?
Yeah, sure.
The more straightforward way is partitions. I know that an equivalence relation is equivalent to a partition. Let's find out what partition is forced on this set from these relations. This says I have one set 1, 2, 3, 4, 5. If I know that 1 is related to 2, and I know that 1 is related to 3, that means the partition containing 1 must also contain 2, and it must also contain 3. Now, 1, 2, and 3 don't appear anywhere else, so I'm going to make a partition containing 1, 2, and 3. Second of all, I know 4 and 5 need to be related, so I'm not going to split up this subset at all. So I claim that just by looking at the things that are demanded to be inside my equivalence relation, I can make a partition of the set. And now I know that associated to this partition is an equivalence relation. As long as this is what's called the coarsest partition associated to these relations, like I haven't subdivided any further. Like a more fine partition would be like splitting these up. But that's not forced on me by the thing. I'm just saying one has to be related to 2, one has to be related to 3, so all these elements have to be in the same set, and 4 is related to 5, so those two have to be in the same set. Once I have my partition, I just add in all of the possible things. 1 needs to be related to 1, 1 needs to be related to 2, 1 needs to be related to 3, 3 needs to be related to 1, 3 needs to be related to 2. Like once you have all the partitions, you just add in all the things that are necessary from the partition. So 1 3 3 1, 1 2 2 1, 3 2 2 3, 1 1 2 2 3 3. Now you have all the things associated to this partition. Then you also need 4 5, 5 4, 4 4, 5 5. So for me, it's kind of very simple to see what the equivalence relation needs to be once I write down the partition that is forced on me.
That makes sense.
So this is maybe an easy way to see kind of this would immediately like if I just do this and start going, I'm going to very naturally come up with both 3 2 and 2 3
Okay.
in my view,
Mm-hmm.
without having to actually look very carefully, like, oh, is such and such in there, you know?
Mm-hmm. Okay. Thank you. That was the one question I had.
Yeah, sure. Any other questions? And you can ask questions about earlier stuff like relations or about stuff on the test or whatever you'd like.
Yeah, would you be willing to go over a problem on the test?
Oh, yes. I actually, I don't know if I can do that right now, just because there's one person who has not taken the test yet and they're about to take it. So unfortunately, I have to retract what I just said. Sorry, but I can go over the test on Thursday.
Right. Yeah, thanks.
Sure. Frank, any questions? Well, just let me know if you have any questions. I'm gonna probably stop recording if there aren't any questions, so.